Hello, party people. Welcome back. I'm just going to jump right back in where we kind of finished up in class. I'm going to finish talking about electron transitions. Okay, so it's a thing. It happens with the UV and the visible spectrum. And when when it has a certain amount of light that is in the UV visible spectrum, then the electrons are able to actually jump from their ground state electron configuration into some higher suborbital. Not a permanent change, but a temporary change from having more energy. The photon, whatever that light source is, has to have more energy than the actual gap. Then the energy it's absorbing is going to help it get up to this level. So the photon needs to have enough energy, not enough energy, to be really clear, high enough energy photons to get up to the next spot. So it's not about amount of photons, it's about having enough energy in that photon hitting it that it can actually make that jump. We say that our energy levels are quantized in an atom. So what that means, certain quantities, there are only certain energies in an atom, right? The orbitals, the rings, if we're thinking Bohr model, there's no half orbital. So if an electron is going to jump, it has to actually go to that next orbital. There has to be another spot available with that amount of energy that it can get to. So yeah, they're very specific, and we can kind of tell things about our actual structure. I have a orbital that has this amount of energy, or there's this amount of energy difference in this ring versus this ring. It's telling us something about that. So you make sure your actual photons have to have enough energy that they can overcome that to actually do electron transitions, or have enough energy for the available electron transitions for them to actually jump orbitals. So here's an example. Of course, pause. Think on your own first. But we're comparing two different atoms, atoms, yeah. N2 versus I2. And we see that N2 absorbs UV and not Vis, but then I2 absorbs both. Why? So, kind of like we were practicing with today. I see evidence, I see the reality. Can I work backwards and explain that? Might not be predicted, but see if you can justify it. Or explain it, I guess. So let's think about this. What is happening when we're absorbing UV and when we're absorbing visible? In both cases, both of those types of radiation cause electron jumps, electron transitions. Or I guess I should say it can. It depends on their energy. But somewhere within that range, they are able to. Cool. So that is what that is what is happening if this type of light gets absorbed. But we're seeing that the N2 doesn't absorb visible light. So why not? It's because visible light does this, and it's not able to do that in N2. So N2 is not absorbing visible light, which has lower energy than the UV light. Okay. So it's absorbing UV, it's doing jumps, but it's not absorbing the low energy visible light. So what's that telling me? It's telling me that I'm doing big energy jumps, but I don't have the specific energy needed, or I don't have jumps available where I would absorb any of that actual visible light. It's just passing through me. It's not doing anything. It's just going off to the next thing where it can do some actual work. So that means that the N2 I don't know. What should I say? Its structure You can just say N2, I guess. Must not have lower energy subshell electron transitions. Available. Okay, so the type of light absorbs tells you kind of like what properties the atom or whatever is able to kind of express, I guess, and like you know that they're going to express it as an electron transition or as visible motion, or sorry, rotational motion or vibrational motion or whatever. Like you know what that light's going to do, but that molecule ain't going to be rotating if it doesn't actually interact with microwaves, or in this case, if it doesn't interact with visible light, it's not going to have that type of electron transition. So yeah, we'll kind of see here, like I mentioned absorbance spectrum when we talked about spectrophotography, photospectrometry, excuse me, where you just kind of shoot all kinds of wavelengths at it, and we see like which ones interact with it. That's important because it kind of tells us something about the structure. Like if it's absorbing a certain type of infrared, then it has certain types of bonds that vibrate a certain way. If it's absorbing a certain type of UV, it has certain types of electron transitions available. So that's what this one down here is kind of showing. We have an example of a substance, and then what effects do we expect? What like properties do you expect to see when it's interacting with light? So let's see. We can see these have the Y is absorbance. So if there are peaks, it's saying that at these wavelengths that we call ultraviolet wavelengths, there is an absorption of light. So think about the type of work that each of these types of light do. So I know ultraviolet, that's high energy and electron transitions. So we would see some of those. We wouldn't see any lower energy transitions possible, but I'm also absorbing some infrared, and we know that infrared does vibrational movement. And also microwaves. So if it's absorbing microwaves, you know that the thing that microwaves do is rotate. And you don't need to worry about the rest of that. But yeah, knowing each type and what they do is important. Cool. Let's talk this. Photoelectric effect. I wanted to mention, this is not that relevant for this class. If this goes over your head, it's not a big deal. But if we're going to be talking about photons, it's important to kind of understand like what we mean by that. Like, if you've heard of a photon before, like we're talking about one particle of light. Photon is like, yeah, it's like a measurement, like it's like one light. But like we actually think of it as a particle. Like you draw a photon as a particle. So we think of it like, oh, it can be in one place. It can be like counted and measured, a photon, a particle. But also, it acts like a wave sometimes. And waves are not the same as particles, one would think, right? Like, particles have like a distinct location and these distinct properties versus waves, which can be described with like having wavelengths and stuff. So, really weird thing that was discovered back in the day that there's lots of cool experiments about it and that kind of stuff. But that's just a thing. We realize that when you have something so tiny as a photon, physics stops working. That's the whole field of like quantum stuff. Like all that means is you're looking at so small stuff, so small it acts weird. So super tiny stuff. Acts like a wave, like a particle, and like a wave, depending on the context. So again, not something you would ever have to explain for this class, but we're gonna be using a lot of different things to describe photons. Something like if anyone actually knows quantum mechanics, my professor from college is definitely going to be like, no, 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 no. But like, I think of it as there's a particle and it's moving like a wave, which, you know, for the sake of this level, is fine, I think. So when we talk about light, we're talking about like you can think of it as like one light at a time, one photon at a time. But it's also going to have a certain wavelength, a certain frequency, and all those kind of properties that a wave would have. It's just something to mention. If you're curious about that, let me know and we can talk more about it later. But it's really not that relevant, so I'm going to try to move on. So based on that, since these waves / particles have these properties, there are also some equations. Like we could do math and like consider like, okay, well, how much energy per photon? How much energy over time? What's the wavelength? And we're able to actually relate those different properties. So these are all on your equation sheet, but I'm going to write them out. We know that E is equal to H, weird V. This equation, where E is represented by representing energy, we're going to put that in joules for reasons that will become clear, I hope. H is Planck's constant. Again, on your equation sheet, which is 6.626 times 10 to the negative 34, of course, joules seconds. So again, on your equation sheet, but if you see H, that's what it is. Notice J and J, it will not cancel correctly and you will get the wrong number if you use kilojoules or something like that. Make sure your time is in make sure you're using this. V is frequency. Again, please make sure that your units are actually canceling out. Frequency is measured in seconds, -1. To clarify, if you haven't seen that before, that means that it's like denominator, like it's in the unit S is in the denominator, inverse seconds. So make sure you make it into seconds if you're given it in another unit, because this is how this all cancels out. So that's one thing. You could also do some rearranging of this equation if you wanted to solve for frequency. Yeah, the other big equation we know is that C is equal to lambda, weird V, where C is the speed of light. Again, on your equation sheet, I think of it as 3, but we can say this times 10 to the 8 meters per second. This is wavelength. Again, put your units in your math, please, 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 because you won't remember to put that in meters so that it matches this meters, or a lot of you would miss that if you don't make sure your units are obvious in your work. And then again, frequency. Inverse seconds. Okay, all that's on your equation sheet. You just need to know when to apply it. You could do a little combination here where you solve for frequency and you plug it in on the other equation. So like a derivation you could do is this. I don't think that one's on your equation sheet, but hopefully you could figure that out if you ever needed it. I'll go try it if you need. Awesome. And then there's something called the photoelectric effect. We've kind of already, like, you can think of it as ionization energy, basically. The photoelectric effect is when a photon, or it's closely related to ionization energy, a photon has enough energy can actually remove an electron. And what do I mean by enough? I mean enough to overcome the binding energy, enough to overcome the ionization energy of actually removing that electron. I think that's fair. Someone who is more involved in the field might disagree with me, but I think that that is a reasonable way of thinking about it. So like, let's look, and there's a lot of math for this type of topic. You could be asked to calculate the amount of energy needed. You could be asked like, does it have enough energy? Yes or no. If it has this wavelength, what's the energy? That kind of thing. Like for example, let's look at this one. PES spectrum of an element in its ground state. Calculate the wavelength of the energy needed to remove a valence electron. So hopefully we'd all be able to recognize this one's the valence. And it says here that our binding energy for the valence is that. So I have energy, binding energy, and I want to make it into wavelength. So think of an equation that could do that. And maybe you remind yourself, oh, hey, my two equations are this and this. And if I do a little rearranging, I could write this as this, where I know everything and I want to solve for lambda. So we could rearrange that further, make it easier on ourselves, move that over, do some multiplying, and you get, do I disagree with myself? No, I agree. So multiply the lambda over, divide by the energy, that. Cool. Again, this is all on your equation sheet. You could try it on your own if you want, but I know that my speed of light is, my speed of light is 2.998 times 10 to the 8th meters per second. And I know that Planck's constant h is 6.626 times 10 to the negative 34. And the units on that is joules per second. Boom. And then, oh, I need to remind myself of something, sorry. Moving on. And then it says right here, the energy I'm trying to overcome is this amount of binding energy. So that's what we would plug in for energy. Joules. Oh, sorry, miswrote this. I was wondering why the units were being weird. On Planck's constant, it's joules times seconds, and on the speed of light, it's meters per second. So seconds on the top, seconds on the bottom, go away. Joules on the top, joules on the bottom, go away. We're solving for meters. You plug it in a calculator. Maybe you test that to see if you can figure out how to use your calculator properly. And we would get this with 3 significant figures. So that's meters. A lot of the time this is given in nanometers. So make sure you check your equation sheet and do that conversion if you need to go to nano, using those metric conversions. Okay, sorry, trying to keep my word and keep this brief. Beer's law. It's Beer-Lambert. I don't know why I don't give Lambert his followers, but I don't know, I always call it Beer's law. This is what our lab is going to be dealing with, so I want to make sure I give you an overview to make it help ensure you are more successful during the lab. So, what is going on in this type of experiment? This is photospectroscopy. I guess I'll make that explicit. Oh no. Certainly not, but you can go fix that on your own. I'm moving on. This is the main way we deal with data from that type of experiment. So what the heck do? We have something called a spectrophotometer. So that's what the machine is called. And inside the spectrophotometer, there's a lamp. And the lamp is emitting light. And the light is going this way. And so it's kind of up to the experimenter how they set up this lamp. What we'd do first usually is we would have it emitting all types of light. Usually we have visible light ones. The fancier ones can do visible and UV. The fancier ones can do even more, but oftentimes we're talking about visible light. And then you put a sample in your machine, and we put it in one of these little containers that is called a cuvette, because it's almost like whatever, it just is. And so this is our sample. And as this light is passing through, some of the light is going to be absorbed by the sample, and some of it will get to like come out the other side. So let's say all these different types of light are hitting it, and the top one and the bottom one get absorbed, but then one more passes through or something like that. Or all of the light from the lamp, and then like only a certain amount of the light gets to go through, depending on what the application is. And then there's a detector at the other side of the machine. Which wavelengths got to pass through. So it knows that it put out all of the wavelengths, and then the detector reads, oh, only this one actually got through, so the rest of them must be absorbed. So transmitted, that's the opposite of absorbed. By the sample. So that's what it's actually reading, and then the machine will often do this for you, but if it's telling you what was transmitted, you can like ascertain which ones were absorbed. Sometimes the machine will just tell you how much was absorbed. That's what we'll use. Okay, so that's the basic setup of how it works. Lamp, sample, detector. I'm like, this procedure I've just written out is how you get an absorbance spectrum. Absorbance. The machine, this is how the machine works, lamp, sample, detector. But this is one type of thing to just get the absorbance spectrum. So what wavelengths does it like? What wavelengths does this thing absorb? And then, yeah, I'm gonna throw this here. Sorry, you can put it somewhere else. But I think it's worth clarifying that like that's one type of the experiment that we kind of do that first to just see what type of light it interacts with and know how it behaves, like that example we looked at earlier. And then what we might do with that, and what we'll be doing tomorrow, is you could choose to set it to a certain wavelength. So maybe I'll just write it in a different color. Okay. So if I realize my sample absorbs light at 450 milliliters, or sorry, nanometers, I could choose to set my lamp like that. And so let's say it's all this type or something. I don't know. I guess these aren't really necessary to draw. And then again, some of it gets absorbed, maybe some of it doesn't. And the detector could tell us, like specifically, like, you know, you can kind of get this from the absorbance, but let me just write it out. Detector reports how much of the light Okay, so looks really similar. What I'm trying to clarify is you could get a spectrum and you could determine like, oh, what types of light does my thing absorb? But then our main application of this, and what we're going to use the thing called Beer's law for, is actually being able to study a sample, and using this data, we will be able to tell what concentration of substance we have. So I guess I'll call this a Beer's law experiment. So specifically, it's usually with dyes, with colored things. So like, we'll know that let's say I have a mixture of like green things and purple things in my sample, but I want to specifically look at how much of the green thing there is, or I just want to know how much of green there is in the sample. If I only have it set to the wavelength that the green stuff absorbs, then I can specifically focus on how much of that absorbs. And the trick of that, the whole thing about Beer's law, so back to what I had on the paper earlier, is there is a direct relationship between concentration and how much light was absorbed. So this, actually setting it to a certain wavelength and focusing in on one of our particles, one of our colors or whatever, allows us, allows us to relate absorbance data and turn it into concentration data. So super simple equation. We have A equals epsilon B C, where A is your absorbance, a unitless value, B is the path length, of our little container of this guy. And the thing about that is we get to design the machines. So we have standardized those, and they're always 1 centimeter. This C is the concentration of the sample. Sample. And then epsilon is something called molar absorptivity. So that is a property of your substance. Okay, so there's a direct linear relationship between absorbance and concentration, and by taking into account how much light the substance absorbs per molar or per mole, we were able to translate between the two. So that's cool. We'll do more with this, but that's the basics of it. There's this linear relationship. So we're gonna do the most common experiments, and you'll get to deal with your own data. But if this is a linear relationship, if you have certain known concentrations, and then measure absorbances, here's your Y, here's your X, and you could actually make a linear graph of this, such as the one in this next example. So you can see that our concentrations on this axis, so they had known concentrations that they graphed against the absorbances. And then we could use that to make predictions, right? So when it was 0.5 concentration, Okay, so sorry, I have an unknown concentration, I know my absorbance. So you could use a graph. Hopefully you could pause and figure this out on your own. But I could see where it hits my graph and then make a prediction about its concentration using that, its molarity. So this is the kind of experiment that we do this kind with, focusing on one absorbance so that we can focus on getting that more precise values for your concentrations. If you did this one, then you get all different types of wavelengths. So 2 different types of graphs using the same machine. You could practice reading this graph as well, please. Wavelength on our X, absorbance on our Y. So, try it on your own first. But it's asking what would be the most appropriate wavelength to gather further absorbance data on. That would be whatever the highest point would be, the lambda max of your graph. Again, because if I know my sample interacts really well and absorbs that type of light the best, I can make sure I'm looking at my sample and not the water or any contaminants or any other colors. I'm just focusing on that one molecule that absorbs in this one way. I don't know, 620-ish, I believe. You can check your axes. And then a concept, maybe you've heard, maybe you haven't, is that the color our eyes see is opposite, complementary to the light actually being absorbed. So some light is absorbed, and then the not absorbed reflected light is what your eyes see. So this graph, it says it absorbs in this range, so like 620. And it says here that that is in the orange range. So it's absorbing in the orange range. But then the complementary color to that, the not absorbed lights, the reflected lights, would be primarily blue in the blue range. Okay, so that's some things to think about. Please do your pre-lab. Hopefully this was helpful. Sorry to make you have extra things to do at home, but you got this.